Watch what happens to this chat window when I sever the physical connection to the internet. It keeps typing. There are no back-end servers, no API keys, and zero data leaving the device. The prompts are processed entirely inside the local browser. This is orchestrated by an open-source library called WebLLM. To build this yourself, you only need three things: a text editor, a local development server, and a modern browser that supports WebGPU. By utilizing the user's hardware, we can shift the heavy computational workload away from centralized data centers and run it directly on the machine sitting on the desk. Step 1 is setting up the interface. In your index.html file, create a drop-down menu for selecting the model, a progress bar to track the initial download, and a container to hold the chat history. We'll apply some basic CSS to give these elements a clean, readable layout. Now, in your JavaScript file, import the create_mlce_engine function from the WebLLM package. This is the core module that powers the application. Before we load anything, we write a gatekeeper check. If navigator.gpu returns false, your code must gracefully block the app and display a warning. WebGPU is a browser API that acts as a bridge. It gives JavaScript direct access to perform massive parallel matrix math natively on the system's graphics card. Because browser support for WebGPU varies and user hardware is incredibly diverse, verifying GPU access upfront is the single most critical step to prevent the application from crashing silently. When the user clicks the Load Model button, we initialize the engine. This sends a request from the main thread to a background worker, which reaches out to a remote repository to fetch the model weights. We pass an init progress callback function to update our progress bar while these heavy files download. The browser caches these weights locally in IndexedDB, meaning they never need to be fetched from the network again. This chart compares the video RAM, or VRAM, required for different models. A large model like Llama 3.1 requires nearly 5 gigabytes of VRAM. If you attempt to load that onto an older device, the browser tab will run out of memory and crash. To guarantee a successful first run, set your default model to small LM2. It requires less than 400 megabytes of memory and initializes very quickly. Developing AI for the browser requires managing this exact balance. You must choose a model capable enough to handle the prompts, but small enough to fit within the physical memory limits of the user's hardware. With the engine running, we capture the user's text input, append it immediately to the chat UI, and hand the prompt over to the model. We construct the API call using standard JSON formatting. The most critical setting here is this flag, stream set to true. Instead of waiting for the model to generate the entire response in the background, we use a for-await loop to catch individual tokens exactly as the engine produces them. Inside that loop, we grab each text chunk and append it directly to the assistant's message bubble in the document object model. Now we can test it. Type a prompt, hit enter, and the model types out its response word by word in real time. Notice that the interface remains completely responsive while the text streams. This is why keeping the engine in a background web worker is necessary. Running heavy computation on the main thread would freeze the page entirely. By feeding the user fragments of text immediately, the wait time is masked. Latency drops away because the user is occupied reading the generated words. For the final test, I will turn off the computer's Wi-Fi completely and ask the AI to list 3 US states. Native benchmarks for these models reach roughly 89 tokens per second, yet this WebGPU implementation consistently hits around 71. That means we're seeing roughly 80% of native speed achieved directly in a web tab. From here, you can browse the MLC catalog to swap in larger quantized models, or implement service workers to convert this code into a fully offline progressive web app. Deploying language models no longer requires renting cloud infrastructure. If the user has a modern browser and a graphics card, they already have the infrastructure to run intelligence locally.